There you go.
So thank you very much, Audran, for the introduction. Thank you, Martina Kramer, for the invitation, and thanks to all the ICCP Journal Club organizing team. So I'm Thomas Lesigne from Latmos, and I will present you the topic of this presentation is the thin tropical tropopause layer cirrus clouds observed by balloon-borne Lidar. So I also thank my co-authors that are also my supervisor, my thesis supervisor, Aurélien Podlagen and François Ravetta. So here is the content of this presentation. I will briefly introduce the tropical tropopause layer, the clouds that live there, and their impact. Then I will introduce the Strateoli 2 project and the BeCool micro LiDAR. Then comparing BeCool observation and Calliope observation, I'll show how the micro LiDAR revealed the extensive coverage of ultra-thin TTL cirrus clouds. Then moving on to my second study, I will show our estimation of TTL cirrus lifetimes. And finally, as a perspective, some preliminary works or directions about the interplay between dynamics and microphysics. So let's start with a general introduction. So the tropical tropopause layer, or TTL, is the gate to the stratosphere. Indeed, in 1949, Brouwer first described the large-scale overturning circulation of tropospheric air masses that rise into the stratosphere along the equator, then slowly move polewards before sinking back to the troposphere at higher latitudes. So the tropical tropopause layer is a transition layer in the tropics in between the troposphere and the stratosphere. And it's really the gate to the stratosphere as the processes occurring there, the different chemical and physical processes, will have an impact on the whole stratosphere. So in the TTL, we find different types of clouds. For example, deep convective clouds that supply water vapor to the upper level of the troposphere, and different types of cirrus clouds that can be either detrained from the convection, so remnant of the anvil part on top of the convective clouds, and this cirrus survive long after the end of convective activity. And those, we also find cirrus clouds that are formed in situ, triggered by dynamical perturbations such as gravity waves, for example, as you can see here. So those clouds impact both the Earth's radiative budget and the lower stratosphere water budget. And actually quantifying this impact is still an open question. So here, to illustrate that, here is on top regarding the radiative forcing of these clouds. Here's a figure from Wang and Fu in 2021 that compares the long wave cloud heating. So this picture is an annual mean, zonal mean, and it's at the level of the tropopause or around. And the long wave cloud, they compare the long wave cloud heating retrieved from the A-train observations, so from space, and in reanalysis, in ERA 5 and ERA 2 reanalysis. And we see this huge gap in the tropics with the reanalysis having struggling to reproduce the long wave cloud heating, and actually even the sign of the cloud heating is different. And the author of this study attributes this gap to a lack of thin TTL cirrus in reanalysis. And this lack of TTL cirrus in reanalysis is itself attributed to a lack of observation of such clouds. On another topic, regarding the modulation of stratospheric water vapor, here is a picture from an article of 2010 from Solomon et al. And they showed that we observed a decrease of 10% in lower stratosphere water vapor content in between the last decade of the previous century and the first decade of our century. And this is a small decrease because 10% this is going from 5 ppm to 4.5 ppm. but still it has a significant impact on the climate. But the climate models do not capture the variability of the stratospheric water vapor in the, and so it is thus necessary to better study the TTL processes and the different type of clouds living there. So here is a brief and incomplete overview of a different type of LiDAR observation of laminar TTL cirrus. So as far as I know, the first observation of such clouds were reported in 1977 by Ute and Russell from a ground-based LiDAR in the Western Pacific Ocean. Such clouds have been observed from airborne LiDAR during different campaigns. Here are from CEPEX campaigns and TOGACOR campaigns. On the right are observations from the APE-TZO campaign. And those clouds have also been observed from space. Here is a picture from LIGHT, the LiDAR in Space Technology Experiment. The first spaceborne LiDAR that ever flew. It flew on board the space shuttle. And actually, this kind of observation was one of the first results from this LiDAR that revealed this thin laminar cirrus extending for thousands of kilometers in the tropics. So those clouds are also seen from the spaceborne LiDAR Calliope, and here is an example from a study in 2019. But all those observations suffer from different kinds of limitations. For example, ground-based LiDAR are intermittently blinded by lower clouds, and they have a very poor spatial sampling. Actually, it's a unique point. Airborne LiDAR have a better spatial sampling, but their temporal coverage is really limited. And if a Calliope spaceborne LiDAR have flown for 17 years, it's flying so far from the clouds that it's struggling to capture the thinnest clouds. So an alternative is to use stratospheric balloons, and that's when I introduced the STRATEOLI2 project. So the STRATEOLI2 project aims at observing the TTL using long-duration superpressure balloons, that type of balloons that are about 12 meter diameter when they are at their flight level. And those balloons carry different sets of in situ or remote sensing instruments. And they drift with the wind in the lower tropical stratosphere at about 20 kilometers. So the STRATEOLI2 campaign already took place. And here is a map of the first campaign, the technical campaign, in winter 2019-2020. So among the 8 balloons that were released, one was carrying a micro LiDAR. And below is a map of the first scientific campaign during the winter 2021-2022. And among the 17 balloons that were released, 3 of them were carrying the BeCool micro LiDAR. So this instrument, BeCool stands for Balloon-Borne Cirrus and Convective Overshoot LiDAR, has been designed at Latmos for STRATEOLI2 project. It's a lightweight and low power LiDAR because it's only 7 kilograms for 10 watts. And it's a very simple LiDAR. It's an elastic backscatter LiDAR with only one single wavelength of 802 nanometer, no depolarization channel. But this instrument provides high resolution measurement with a vertical sampling of 15 meters and a native temporal resolution of 1 minute. This instrument only operates during nighttime with a duty cycle of 10 minutes on and then 10 minutes off for cooling, for thermal constraint on board the gondola. So what are we looking at with this instrument? Here is an example of 12 consecutive nights it's the first flight from the 2021-2022 campaign. So the balloon starts on the left of the picture and moves to the right. It's flying on top of the picture at about 20 kilometers, and we can see the ocean surface at the bottom of the picture. and the different type of clouds that are overflown by the balloon. So here is an example of a nice thin cirrus very high in the TTL. And we also see a bunch of details, for example, in the maritime boundary layer. So this is only 12 nights, but during this campaign, we have a total of 137 nights of observation, which is about 40,000 one-minute LiDAR profiles. And here is the 12 nights that I showed just previously. And the first flight only lasts for 12 days, while the second flight lasted for about 40 days, and the third flight about 70 days. And we see on the flight 2 and 3, we see a huge contrast in between the first part of the flight, which are really cloudy, with clouds that are totally attenuating the LiDAR beam, so that we attribute this kind of behavior to very opaque clouds, so to convective clouds. And the second part of the flight are less cloudy, with more clear sky and only very high clouds. So those are the typical conditions above the Pacific Ocean during the campaign. Yes, this is the overview of the full campaign. So the first thing we wonder when we have this observation is how does it compare to Calliope observations from the satellite Calypso. So here is the first case study of collocated measurement of Be Cool and Calliope. So actually the satellite really fly above the balloon and across this track. So on ground, the distance on ground at coincidence is less than 200 meters. On this map, this is about 500 by 500 kilometer map. The balloon is flying along the solid line here, and the satellite is flying along the dashed line here. So the LiDAR curtains observed with the balloon is displayed here in the center, and it's about 11 hours of observation. The LiDAR curtain along this dashed line here is displayed on the right, and it's only 1 minute of observation. So we see that at coincidence, which is this white line here, both instruments are looking at the very exact same scene, so with a 6 Cirrus on top of 2 mid-layer clouds. And the retrieve optical depth of these 6 Cirrus are in very good agreement at coincidence, and it's about 0.4. And on the right, you can see the LiDAR profile closest to coincidence at comparable horizontal resolution. So it's about each profile is about 5 kilometers on the ground, and to achieve such horizontal resolution, Be Cool observation can be integrating up to 10 minutes, while Calliope observation are integrating less than 1 second. It's only 15 LiDAR shots. And so this very long integration time enables us to have a very good signal-to-noise ratio that can be seen here. So, we see a very noisy profile on Calliope and no noise here, basically. So here is another case study of collocated observation, but this time over a very thin cirrus cloud. And indeed, so again, this is a 500 by 500 kilometer map, and the balloon is flying along the solid line here, the satellite along the dashed line here. And on the Be Cool curtain, we see very clearly a very thin cirrus at 17.5 kilometers that appears with no ambiguity. While on Calliope curtains here, we also see this long and thin cirrus, but we see that it's more or less hidden in the noise. And the official level 2 product of Calliope that reports cloud properties such as optical depth, cloud top altitude, cloud base altitude, only report these clouds in the small white box here. And so the algorithm, the operational algorithm, is missing most of its horizontal extent. So if we zoom on the profile in between 16 and 19 kilometers, we see this cloud really clearly on Be Cool profile, and while on Calliope profile, they are more or less hidden in the noise. So another thing is beyond the difference in signal-to-noise ratio that is attributed to a different integration time. As Be Cool is operating at 800 nanometers and Calliope at 500 nanometers, the relay scattering is weaker for Be Cool in the near infrared, which means that there is a higher contrast in between the cloud and the clear sky around the cloud. So this feature was reported previously by Peter et al. From the APTCO campaign, where they described quite nicely these ultra-thin tropical Tropopause clouds. And we see here on this figure from their article of 2003 that the signals is, the scattering ratio is really clear. The cloud appear really clearly in the infrared, while at 500 nanometer, it's almost not present on their observation. So this ability of Be Cool to detect very thin clouds can also be seen from a statistical point of view. And to do so, I computed statistics of cloud optical death for during the 3 flights of Be Cool, and from each Calliope nighttime overpass during the campaign over the same area. And we see on this distribution of cloud optical death that there is a very good agreement on the right-hand side of this plot, down to this limit where there is a clear cutoff in Calliope optical death distribution, while Be Cool really extend the distribution below this threshold of 2 to 10 to minus 3. So this is actually the detection threshold of Calliope. And with Be Cool, we see about 27% of clouds below this threshold, while it's only 0.5% of clouds for Calliope. So now if we look at the cloud top altitude and cloud base altitude of those clouds, those clouds on the left-hand part, those really thin clouds that are not detected with Calliope, we see a clear peak up in the TTL. And so those ultra-thin TTL Cirrus, which have a base altitude above 14 kilometers and an optical depth below 2 to 10 to minus 3, are detected in 23% of the profile, which is about 1 profile over 4. So it really changed the way we see the cloud coverage, and it's a significant amount of clouds that were not detected by Calliope, that are not detected by Calliope, actually. So those results, those different comparisons were published last year in my first paper, and thanks, I thanks all the co-authors of this paper. And now let's move on to the second study. So our second study the idea is we want to take advantage of the slow motion of the balloon over the clouds to estimate their lifetime. Indeed, so going back to this picture from light, we see here a 1,000 kilometer long Cirrus, but how long does it live for? It's essential to estimate the cloud lifetime to better understand, on the first hand, the processes that shape these clouds and the relevant timescales to simulate, and also the impact on those clouds on the upper troposphere, lower stratosphere, water vapor budget. Unfortunately, airplanes and satellites are moving too fast, and they only provide quasi-instantaneous snapshots of the cloudy scenes, and they do not. We cannot monitor the evolution of cloudy structures from an aircraft or from a satellite. So that's why the balloon-borne observations are really valuable to follow the evolution of clouds over time. So on this study, we focused on the Central Pacific Ocean. So this is this part of the Flight 2 and Flight 3 of the Strategy 2 campaign. And so it's about 80 nights of observations that were performed above the Pacific Ocean. So on those 80 pictures, we focused on the TTL, so on what is above 14 kilometers. And we detect clouds as continuous patch of scattering ratio above 1.5. And we define their apparent lifetime as the temporal extension of the clouds. So on the left are two examples of two different nights of observation. So on top is the scattering ratio, and below are the detected clouds. So the clouds are classified then in three classes, different according to the way we see them appearing, then disappearing. The fully resolved clouds are those that appear then disappear within the same night. The partially resolved clouds are those that only appear or disappear within the night. And the night-long clouds appear to be there throughout the whole night. So from processing the 80 images in this way, we get a partitioning of the cloud distribution in three classes. So this is the pie chart here. And we also get apparent lifetime distribution for the fully resolved and for the partially resolved classes. So the blue and yellow histograms here. But what we want to estimate is not the partially or truncated lifetime of clouds. We want to have an estimation of the underlying day and nighttime lifetime distribution. So we developed a fitting method to try to find a distribution that reproduce those results. And here is a quick walk through the fitting method. So first, we assume we pick a lifetime, we pick a distribution that we want to test. For example, here an exponential law, let's say, and a strong assumption on this study is that there is no diurnal cycle. Those clouds are evenly distributed within day and night. So we pick a distribution and we take a random sample of lifetimes from this distribution. Then we randomly throw these synthetic clouds on the diurnal cycle and then we apply a day-night mask to remove the daytime and mimic the Lidar observation. So we finally classify what is left the same way we classified the observation. For example, here fully resolved clouds, a bunch of partially resolved clouds, and a few long-lived night-long clouds. So from there we get partitioning in three classes and apparent lifetime distribution for the fully and partially resolved classes. And we built an ad hoc score to evaluate the goodness of fit in between these synthetic results and what we really observed. So this score is built comparing the pie chart and the two partial distributions. So finally, the best fitted distribution was found using a log normal distribution with a median lifetime of 1 hour and a mean lifetime of 6 hours. And you see here on the right that the synthetic. So this is what we get from an extensive random sample from this distribution, fairly reproduce our results. So the pie chart and the lifetime distribution. So we find lifetime distribution that allow that fairly reproduce the observation, but we see, for example, that half of the clouds are shorter than 1 hour. But do those clouds matter? And actually, a parameter that matter for example, radiative forcing is the cloud cover. So and the cloud cover is an integrated quantity. So we investigated the contribution, the relative contribution of short-lived and long-lived clouds to the cloud cover, and the results are here. We see that the 50% of clouds living less than 1 hour will only contribute for 3% of the cloud cover, while the 10% of clouds living longer than 12 hours will contribute to 70% of the cloud cover. So the cloud cover is really dominated by the long-lived clouds, and so the long time scales are relevant to take into account when simulating those clouds. So finally, we wanted to compare those results with the TTL Cirrus lifetime in ERA 5. And in ERA 5, we detect clouds as continuous patch of non-zero cloud ice water content. So we extracted Lidar-like curtains below the balloon, and also from a Eulerian point of view. So on this plot, it's a cumulative distribution. So our best fitted low is the red dashed line here. The lifetime distribution along the balloon track is the dark blue curve here, and the light blue beam is the beam of the Eulerian lifetime distribution seen at each model grid point under the balloon track. And we see that there is a fair agreement in between those distributions, even though short-lived clouds are less frequent in ERA 5 than in our estimate. We also see that the balloon following distribution is well contained within the light blue beam of the Eulerian lifetime, and we see that the mean lifetime along the balloon track is in line with the mode of the mean lifetime from a Eulerian point of view. So we can say that there is a fair agreement between ERA 5 and our estimates, but still there is not enough clouds in the reanalysis. Indeed, in the LiDAR observation, we see 70% of cloudy profile, cloudy TTL profile, or clouds in the TTL, and while it's only 30% in ERA 5 following the balloon. So even though the lifetime of clouds, of TTL clouds in ERA 5 seems to be in fair agreement with our estimate, a bunch of clouds are missing. So to investigate a bit further, here are preliminary results of pixel-wise BCool and ERA 5 comparison. So along the balloon track, I upsampled a little bit the ERA 5 reanalysis to fit the resolution of BCool for this study, which has been coarsened to 250 meters on the vertical and 20 minutes on the horizontal. And here are 3 examples of superimposed ERA 5 and BCool clouds. And we see on the left an example where there is a pretty good match that ERA 5 is putting, so in pink is ERA 5 and in blue it's BCool. ERA 5 puts a cloud where we actually see one. In the middle, it's not that good, but part of this cloud, maybe fortunately, is here. And on the right, it's not good at all, because ERA 5 puts here a cloud that doesn't exist. From a statistical point of view, here is a vertical distribution of cloudy pixels. So in blue, it's from BCool observation. In red, it's from ERA 5. And in pink is the pixels that are both that are cloudy, both in ERA 5 and BCool. And so we see that the total amount of cloudy pixel in ERA 5 is roughly half the total amount of cloudy pixel in our observations. And looking at the distribution of the pixels that are only detected as cloudy by the LiDAR, or those that are detected as cloudy by both by the LiDAR and in the reanalysis. So those distributions are displayed here. So this in the altitude scattering ratio space. And we see, so the blue contours are isodensity contours of Bicool-only cloudy pixels, and in pink are isodensity contours of Bicool and ERA5 cloudy pixel. And we see that ERA5 performs quite well, capturing the lowest and more opaque clouds, so those which have a stronger backscatter. And ERA5 is missing the thinnest and highest TTL Cirrus clouds. So finally, the last part of this presentation is about ongoing work on the interplay of dynamics and microphysics. So there is a strong relationship in between TTL cirrus clouds and wave-induced temperature anomalies. So this relationship was first highlighted by Bohm and Verlinde in a paper of 2000, using radio sounds for temperature and Lidar observation at Nauru Island. And on this picture, we see temperature anomalies in green and yellow, and the cirrus line are detected cirrus. And we see that there is a good coincidence in between cirrus clouds and cold anomalies. So here it's the green anomalies. And actually, there is an ubiquitous presence of wave with downward phase propagation through the TTL, so as depicted by those arrows here. And cirrus clouds occur almost exclusively in cold temperature anomalies due to waves. So this relationship can also be seen in a Bicool curtain with superimposing ERA5 temperature anomaly. So we remove the background state from ERA5, and we see that clouds live in cold anomalies with downward propagating phase. So this relationship was have been previously investigated from observation. For example, here is a figure from Kim et al. In 2016 that investigated it from ATREX campaign, airborne campaign. Here is a figure from Chang and Lecuyer in 2020. They investigated that using Calypso, the Lidar measurement, and cosmic radio occultation temperature profile. And this relationship was also investigated from idealized simulation. Here is a picture from an article from Putglagen et al. In 2018. So it gives the observation gives a good statistical point of view about the correlation of cirrus clouds and cold temperature anomalies. And the simulation hypothesize some processes that are responsible for this correlation. But using Bicool observation, we can go down to really fine scale and taking advantage of the very high vertical resolution and unique temporal resolution of this observation. So this is an example of a highly multi-layered TTL cirrus with very thin persistent high backscatter layers that are embedded within a lower backscatter cloud. We see, zooming inside this picture, we see that those different layers undergo a quite strong excursion, vertical excursion, and we attribute that to waves and dynamics passing by. And actually, this kind of observation is a reminiscent of local spikes in ice crystal number concentrations that were reported from the ATREX campaign, from the airborne ATREX data. So on this plot, in red is the ice crystal number concentration measured along the flight path, and those spikes are quite similar to what we observe. And it's also quite similar to previous Cirrus simulations. Here in a paper from Eric Jensen, we see quite similar structures appearing in colon simulation of TTL Cirrus. But at that time, it was not really commented, maybe because there were no evidence for the reality of such structure. But we see that quite often in BCool observation. So the questions are, what resolution is needed to simulate this feature? What are the implications for Cirrus representation in climate and storm resolving model? Is it a characteristic feature of those clouds? Can we quantify how often do it occur? So this is currently under investigation, combining our observation with Lagrangian microphysics simulations. And so it's the end of this presentation. To conclude, I will say that BCool is a quite unique data set, and this data set will be extended during next Stratoli 2 campaign in winter 2026-2027. These observations have a very high geometrical and optical resolution that allowed us to study ultra-thin clouds thanks to the very high signal-to-noise ratio, and also to look into multi-layered cirrus thanks to the high vertical resolution. The very original sampling of stratospheric balloons allow to follow clouds over time, and it allows us to study or to try to estimate the cirrus lifetime in the TTL. And this is quite unique to the balloon. And finally, the ongoing work is to characterize the interplay between microphysics and dynamics leading to the multi-layered clouds, to quantify the radiative impact of those clouds, and also to quantify their effect on the stratospheric water vapor budget. Thank you very much, and I'll be glad to answer a few questions.